do is turn to the next set of slides, which is on the context for where this kind of training or where this course might fit in with your other expertise. And if you're like me, most of your training in statistics or quantitative methods operates within a frequentist framework. You learn about things like parameters and statistics and estimates of the parameters and standard errors and confidence intervals and hypothesis tests and so on. And in that framework, which is, I think, characterizes most quantitative methods training and experience, Bayesian approaches, to the extent that they're taught at all, are taught as a special topic. And here's a nice quote from Dennis Lindley, who says, Bayesian statistics is not a branch of statistics. It is a way of looking at the whole of statistics. So if you're like me, most of your training did not focus on Bayesian methods, and it was introduced as a kind of a side or a branch or a special topic in statistics. And I really want to encourage you to think, well, I could be doing everything this way. That is, I could approach all of my statistical analyses or data analyses with a Bayesian approach. Why would we adopt Bayesian approaches? There are lots of reasons, and I can really put them into two main buckets or categories. One is philosophical. This is kind of the argument that a Bayesian approach offers us a more coherent way to approaching our modeling, our data analysis, and facilitating our inferences. I find that very persuasive. Philosophically, I am a Bayesian. There's a whole other category of reasons why people might adopt Bayesian methods, which are more practical in nature. And this is saying that if you want to be able to accomplish your ends, sometimes it can be fruitful to adopt a Bayesian approach. Indeed, it can be difficult. And there's no arguing that Bayesian approaches can seem like a lot more work for some simple situations relative to what you might already be familiar with. But I think it is fair to say you can do more with Bayesian approaches. If you want to push the limits of modeling in quantitative methods, very often we want to go with Bayesian methods. So I have colleagues who say, Roy, I don't believe in any of that philosophical reasoning that you care so much about. I don't buy it. It doesn't matter to me. But I want to do this. And in order for me to get my work done, I turn to Bayesian approaches. I say, okay, great. Glad to have you on board. Here is a very strong position, sort of fighting words from Lindley. And if we can excuse the gendered language for the moment, Lindley tells us that every statistician would be a Bayesian if they took the trouble to read the literature thoroughly and were honest enough to admit that they might have been wrong. So Lindley here is saying, look, if we take these ideas seriously, we would all come around to this way of doing things. That's a pretty strong position to take, and I'm not quite going to advocate that, as you'll see. So where does this fit in? What are we going to do in our time together? And how are we going to approach things relative to the context and training that most of us have already had? Most of our training, as I said, has operated within a kind of frequentist framework. Bayesian statistics is not a branch of that. It is a way of looking or doing all of statistics. In order to teach us something new, Bayesian stuff, we will spend most of our time doing it with models and situations that are familiar to us. We're going to start pretty simple with single variable and then two variable normal distribution, build our way up to regression models. My guess is at some point during our time together, you're going to be tempted to say something like the following. Do I really need Bayes to do this, to estimate a mean? Come on, I know how to estimate a mean of a distribution. I don't need any of this Bayes business. We are going to discuss familiar situations like estimating a mean or running a regression analysis, because it'll be easier to understand what a Bayesian approach offers that's new. It'll allow us to see some similarities and differences between Bayesian and more conventional frequentist methods. And if you look closely, you can often see Bayesian principles show up in those conventional methods. On the other hand, I suspect you may be frustrated at times. You might be thinking to yourself, well, actually doing this is kind of hard. I thought this was supposed to be easy or easier than what I was used to doing, or at least doable or tractable. And a nice quote from Don Barry instructs us that Bayesian statistics is difficult in the sense that thinking is difficult. This is going to be challenging in certain respects, either the organization or the execution via software, or what we have to pay attention to. What is our goal? I want to kind of establish what we'd like to accomplish in between two very opposed positions that are more fighting stances. One of those is captured by this quote from Fisher. Fisher wrote that the theory of inverse probability, that's Bayes inference before it was known by Bayes inference, is founded upon an error and must be wholly rejected. So this is Fisher saying, the stuff we're about to talk about, this is wrong, don't do this. At the other end of the spectrum, we've seen this quote already from Lindley, every statistician would be a Bayesian if we took the trouble to read the literature thoroughly and were honest enough to admit that we might have been wrong. These are fighting words at the other end of the spectrum saying we should all be doing this all the time. That's not the position I'm going to adopt. I'm going to adopt more of a position here expressed by Box some 40 years ago. These days, the statistician is often asked questions such as, are you a Bayesian? Are you a frequentist? Are you a data analyst? Are you a designer of experiments? I will argue the appropriate answer to all these questions can be, and preferably should be, yes. So the goal here is to introduce Bayesian statistics against a backdrop that I think many of us are familiar with from our existing training and experiences. The goal here is to get you to think, all right, how would a Bayesian approach this? Or when might a Bayesian approach to this kind of problem be advantageous? Questions or thoughts as we kind of set the stage for what we'll be doing together? Then what we're going to turn to now is a little bit of getting into some of the machinery of things we'll be using, in particular, the machinery of probability. We're going to briefly go through some of the key points of probability, the machinery of probability, because it'll allow us to build some things we'll need. For some of us, we might be very familiar with these ideas. For others of us, this might be stuff we learned in probability class or stats class a long time ago, but haven't really dusted off in a while. And for others of us, this might be the first time seeing things presented like this, and that's okay. Some of the key principles. There are different ways to formulate probability theory. Here's a pretty common one. We're going to start with one variable x that is discrete in the sense that it can take on a finite set of mutually exclusive and exhaustive possible values, little x, x1, x2, x3, up to however many categories or possible values we have. And we have a probability mass function that says, what's the probability of this random variable taking on each state or each particular value? And I can write that probability expression any of a number of ways. I'm going to use this notation interchangeably, usually just using P and X. There are three kind of basic axioms here that we'll use to build off of. One is that probability's got to be between 0 and 1. So if we're doing a calculation and we come up and the probability of something is 2.7, something has gone wrong somewhere. Probability's got to be between 0 and 1. The second one is that if we are just reading that, the sum over all different possible states, the sum of the probabilities has got to add up to 1. That is, if I have things that are mutually exclusive and exhaustive states, the probability of it taking on this value or the probability of this taking on this value, if I add them all up, they got to add up to 1. And then the third one is the probability of the random variable taking on a particular value, say xj, or it takes on a different value, say xm, is just the sum of the individual probabilities for the two of them. That's the rules talking about one variable, x. When we have more than one variable, we have joint distributions. Let's keep it as simple as can be right now. Two variables, x and y. If we read this expression here in the second bullet point, I read that as the probability that x takes on a particular value, xj, and y takes on a particular value, yk. The comma there in between the x and the y can be read as the word and. So it's the probability of this and this. The same rules kind of apply. Probability's got to be between 0 and 1. And if I add up all the different possible, over all the different possible states, the probability of x taking on a value xj and y taking on a value of yk, for all possible values of j and k, all the probabilities, everything's got to add up to 1. When we have more than one variable, we can talk about them jointly, or there are many times where I want to talk about one variable all by itself. So again, let's keep our situation with two variables, x and y. We have the joint probability. That's the probability of x taking on a particular value, xj, and y taking on a particular value, yk. What is the marginal probability? The marginal probability refers to the probability of, say, x taking on a particular value without reference to y. So if we look at this expression on this slide, on the left-hand side, we have an expression just for the probability of x. So this is saying, how do I talk about x all by itself without regard to y? Well, if I know the joint probability of x taking on its value and y taking on its value, I just sum those up over the different values of y. This can be viewed as a marginalization over this other variable y that I want to get rid of. An idea that's going to be super important for us, conditional distributions. This is where we have multiple variables. Again, let's keep it at 2, x and y. And now we want to have the expression here reading across the probability that, say, x takes on its particular value of xj, and then this vertical bar or pipe is read as given that y takes on its particular value yk. Or in a little bit simpler notation, what's the probability of x taking on this value conditional on or given that y takes on this value? We do this kind of thinking and formulation of models all the time, even if we're not explicit about it. We think about, okay, in a medical diagnosis example, what's the probability this patient has cancer given their age, their family history, and whether they smoke? Or in modeling weather and temperature, what's the probability that the high temperature today reaches a certain value given where we are located in the world and what the temperature is like yesterday. This notion of conditional on or given that is vitally important for us in specifying models. An alternative conception of this conditioning is not even that things have to have turned out that way. It's almost a hypothetical, as if certain things were the case. That is, what's the probability that X takes on a particular value if Y were to take on this value? And it has a formal definition. The conditional probability for X taking on a particular value given Y takes on a particular value is equal to the joint probability, the probability of both those things happening, divided by the marginal probability of Y all by itself. All the rules and stuff for probabilities hold for conditional probabilities as long as we're doing the same conditioning throughout. So these axioms here are pretty much the same thing we had, I don't know, 5, 6, 7, 8 slides ago when we talked about the rules for probabilities, only now instead of px in parentheses, it's px vertical bar y. But all the same ideas hold. Given a value of y, the conditional probabilities for x given that value of y, they all got to be between 0 and 1. And at that value of y, all the conditional probabilities for x got to add up to 1. And if we're conditioning on a particular value of y, the probability that x takes on one value or another value is the probability of x taking on each one just added up. Let's put some of these pieces together. How do we connect them? Okay, here's our situation. We got two variables, x and y. If py is the marginal probability for y, that is the probability that y takes on a particular value, yk, without mention of x, just talking about y all by itself. And then px given y is the conditional probability that x takes on a particular value, xj, given that y takes on a particular value, yk. Then, okay, a lot of words coming. The joint probability of a particular value x and a particular value y is the product of the conditional probability for x given that value for y and the marginal probability for that value of y. Okay, that's a lot of words there, but here's the idea. If I know what the probability for y is all by itself, that's all the way on the right-hand side, and I know the probability for x given that y takes on that value, then multiplying the two together gives me the probability of both of those things occurring. If I say I know the probability that it's going to reach 70 degrees Fahrenheit where I am today, and the probability that it rains, given that it reaches 70 degrees Fahrenheit, then I can multiply those two to say, what's the probability that it reaches 70 degrees Fahrenheit and it rains today? One more connection to draw, again, in this same setup or situation, is that if I want the marginal probability for x all by itself, well, as we said, we can think of this as a process of marginalizing over y, where if I want to talk about the probability of x all by itself, I can take the joint probability of x and y and sum over or marginalize out the values of y. But hey, that joint probability we just said is equal to the product of the conditional probability for x given y and the marginal for y. Again, I know for many of us, this is something we maybe haven't seen before or saw long, long ago in probability and stats class a long time ago. Why are we doing this? Well, one reason is these are the ingredients that allow us to derive Bayes' theorem. And we're going to do that right now. We've got two variables, x and y. And the joint probability is what's on the left-hand side, the probability of x and the probability of y. And as we said, we can express that as being equal to the probability of one of those things, y, multiplied by the conditional probability for the other, x, given y. I can do that same process, now just reversing the roles of x and y. So the top line says the joint probability of x and y is equal to the probability of y all by itself times the probability of x given y. The second line says, well, that joint probability is also equal to the probability of x all by itself multiplied by the probability of y given x. This is my favorite line in the derivation. Something is equal to itself. I know that's true. And now I'm just going to plug in from the first two lines into the third line. Okay, so here in this first line, probability of x and y is equal to, let's see, probability of x given y multiplied by the probability of y. I'm going to plug that in on the right-hand side here for this term. And the probability of x and y being, x and y together is equal to the probability of y given x times the probability of x. I'm going to plug that into the left-hand side of this expression. Now, if I want to isolate, what's the probability of y given x on the left-hand side? In order to do that, I got to divide both sides by the probability of x. So I can express this as saying the conditional probability of y given x is equal to the conditional probability of x given y multiplied by the marginal probability of y divided by the marginal probability of x. Or if I wanted to isolate the other conditional probability here, probability of x given y, in order to isolate this one, I would need to divide both sides by the probability of y. Here, probability of x given y is equal to the probability of y given x times the probability of x all by itself divided by the marginal probability of y all by itself. This is Bayes' theorem. We have now derived Bayes' theorem, and we did it on one slide. Just to continue talking about probability theory or the machinery of probability that we will use, everything we've introduced so far has been for discrete random variables, variables that can take on particular values. For continuous random variables, we don't have probability defined for a particular value, but for ranges of values. The full range of a distribution is referred to as the support of the distribution. So if you're like me, one of the first distributions you learned about was a normal distribution, or what's sometimes called a Gaussian distribution. And that has a distribution that has a nice particular continuous shape, and it ranges over the real line from negative infinity to positive infinity. That is the support of that distribution. And in continuous random variables, instead of having a probability mass function, we have a probability density function. For a random variable x that has a normal or Gaussian distribution, there is an equation that describes that curve. All the same concepts we've quickly reviewed. Joint marginal distributions, joint distributions, conditional distributions, Bayes' theorem, notions of independence of variables, conditioning, all that stuff of the machinery of probability all applies for continuous as well as discrete random variables. The only change is in the mathematics. What do I mean by that? Basically, the shift from discrete to continuous is that instead of taking sums, we take integrals. So, for example, one of the first things we said was, for a random variable x that can take on particular values, the sum of all the probabilities, they got to add up to 1. In the continuous case, instead of adding, we are integrating over the support of the distribution. The full integral has got to be equal to 1. And when we had a joint probability, we said the joint probability of x taking on its value and y taking on its value, if I add up all those joint probabilities, they got to add up to 1. Same idea over here with continuous random variables. Instead of adding, if I take the integration, it's got to integrate to 1. For a marginal probability, if I want to talk about the probability of x all by itself, in the discrete case, we sum over the different values of y. In the continuous case, we integrate out y, but it's the same idea. Some additional terminology that we will sneak in here and use a little bit as we're trying to make sense of what we'll do. You'll sometimes see that a distribution is referred to as being proper if it integrates or sums to a finite quantity. A distribution is normalized if that finite quantity is 1. That's kind of what we already said. In order for something to be a legit probability distribution, it's got to sum or integrate to 1. The kernel of the distribution is the part where the action is. It contains the variables and the parameters, the good stuff. A normalizing constant is the part of the distribution that serves to normalize the distribution. That is, make sure that everything integrates or adds to 1. If we drop a normalizing constant, we keep the kernel, we keep the good stuff. What we have is something that is not equal to probability, but is proportional to the probability. Let me explain what I mean with an equation, and then we'll look at some pictures. So down here is the probability density function for a normal distribution for a random variable x. This portion of the distribution is the kernel. This is the good stuff. It has the random variable x. It has the parameters mu and sigma. This other term over here, that's a normalizing constant, 1 over square root of 2 pi, where pi is a number, right? If I write this by dropping the normalizing constant, I got rid of the term bracketed there in red. What I have is not something that is not quite equal to a probability distribution, but is proportional to a distribution. This little funny sign is proportional to. We're going to use this a lot later on, really starting tomorrow. Let me illustrate what I mean by proportionality. And my guess is it's something you're already very familiar with, just expressed in a different way. I'm a picture person, so here's how I think about this issue. Here is a visualization of a normal distribution. It's centered at 0. It has some variability. And I've drawn it going down from -6 to up to +6. But the distribution does go on indefinitely. This is a normalized distribution. If I were to integrate over the real line, that is, look at the total area under the curve, the integral would add up, or the integral would come to be 1. That's what we mean when we say probability's got to integrate or sum to 1. Notice the values along the vertical axis. They're decimals. They're pretty small because the whole space has to integrate up to 1. What is the message of this distribution? Well, if I look at its shape, it tells me how likely certain values are to occur. The message of this distribution, roughly speaking, is, okay, values near zero are more likely. As we move away from zero, either above or below, relatively speaking, the probabilities taper off in this kind of shape. Values near zero more likely. Once I get pushing out values beyond plus or minus 2, it's very unlikely. That's the story of this distribution. Now pretend I take the vertical axis and I double all the values. This will no longer integrate to 1. What is the story of the distribution? It's the same as it was a moment ago. The shape of the distribution still tells me that values near zero are most likely. As I move away from zero in either direction, the probability tends to taper off following the shape of the curve. Well, let me really crank up the values of the vertical axis. This is not going to integrate to anything anywhere close to 1. But the message of the shape of the distribution remains unchanged. Such that if you're like me, pretty early on in your statistics training, when you were drawing these pictures, drawing these curves, I didn't even bother to write in the values along the vertical axis. I actually don't know if this thing is going to integrate to 1 because I don't have the values along the vertical axis, but I don't need them. Yes, I know in order for it to be a normalized distribution, it's got to integrate to 1. But the shape of the curve is what tells the story about what values for the variable are likely, what values are unlikely. So we're going to be using this notion of proportionality a lot later on. What I want you to get across, or what I want to come across right now is something that is proportional to a normalized distribution still conveys the meaning. Which values are likely, which values are less likely. Quick summary of what we've been doing so far. We have quickly reviewed ideas about the machinery of probability, some of the axioms. We've introduced things like joint distributions for more than one variable, marginal distributions. That's when we have many variables, but we want to talk about one without mention of the others. And conditional distributions. That's when we have multiple variables and we want to talk about one given the other variable. We introduced Bayes' theorem. We derived it in what? I think 6 lines of equations, 4, 5, 6 lines of equations gave us Bayes' theorem. And then we've introduced things like continuous random variables, which have the same concepts, but integration instead of summation. And then this idea of proportionality to a distribution. This has been a quick kind of overview. Again, for many of us, this is things we've maybe seen before, but perhaps not in a while. For some of us, maybe this is the first time seeing it in this way. Thoughts or questions? I'm going to hop over and call up the next set of slides. Which has to do with the interpretations of probability. So we just talked about the machinery a little bit. Now I'm going to introduce some interpretations of probability. And these are going to be 2 interpretations that we'll mention of others. We're not going to cover all different possible interpretations. We're going to cover 2 big popular ones, and we'll talk about why. The first interpretation is what's sometimes called a frequentist interpretation or a chance interpretation, or it goes by other names as well. And here's a quote that captures the idea about what probability means or where it can be applied. Von Mises wrote, the rational concept of probability, which is the only basis of probability calculus. We just reviewed probability calculus. That was all those expressions in machinery. So the rational concept of probability applies only to problems in which either the same event repeats itself again and again, or a great number of uniform, that is, same elements are involved at the same time. So something repeating over and over again, or a great number of the same or uniform elements. Okay, let's work our way into this. So from this grounding, we understand that the outcomes or the results of many repeated instantiations or many repetitions of something, they will vary, they will differ in an unpredictable manner. We call this random variation. However, over many repetitions, long-run regularities emerge. We take repeated observations of the same event over and over and over and over and over, and we count up the number of times that a particular event occurs in that set of observations. There is a relative frequency or proportion here, the count divided by the number of observations. And this relative frequency will tend to stabilize or converge as the number of observations goes to infinity. These stable, long-run relative frequencies characterize the situation. They tell the story. We assign a number, and we call that number the probability of the event occurring, to stand for this long-run, stable, relative frequency. Okay. Here's the idea in a picture, a little simulation of something. This is a plot of the proportion of successes in a series of Bernoulli variables with probability of success 0.6. We'll talk about Bernoulli variables a little bit more today, later on. But just think of this as a coin flip, that it can either land on heads or tails. But this is not a fair coin. This is a biased coin. This is a coin that in truth is biased in favor of heads, such that it'll land on heads with probability 0.6. So it's not a fair coin, it's a biased coin. Yeah. Down here is a plot of the running relative frequency, or the running proportion of heads of many flips of this coin. So the first flip of the coin here was a tails. So it was 0 out of 1. So the proportion was 0. And then the second flip of the coin was also, was then a heads, and then tails, and then heads, and so on. And you can see what is at a few flips of the coin, 50 flips of the coin, 100 flips of the coin, 200 flips of the coin, all the way up to 1,000 flips of the coin. What is the proportion of heads after a certain number of flips? Well, it starts off way down there at 0 because the first flip was tails. And then it bounces around and it goes up to 0.6 and it goes above and it goes below and it wanders and around and around. But eventually, over the long run, it stabilizes at a limiting value. And we call that limiting value the probability. And sure enough, it's right smack dab there at 0.6. Under this interpretation of probability, the value, the magnitude, or the probability, say 0.6, is determined by the repeatable situation at hand. It is objective or unique in the sense that it does not depend on the investigator or any other ancillary circumstances. It's a property of the world. In my little example, it's a property of the coin flip. Where is it defined? Situations that are at least potentially able to be repeated over and over and over under essentially identical conditions. What is the relevant information? Observing the outcomes, results of flips of the coin. Or another metaphor I like is widgets off a manufacturing line. I have this mental image of a cartoon where there's a little conveyor belt that spits out products that are being manufactured, and every few seconds a new product comes off the conveyor belt, off the manufacturing line, and we want to see what's the probability of a product being defective. Well, I have many repeated events, and I count up the proportion of times that those products are defective, and that proportion will stabilize over the long run. Historically, we see this notion of probability basically dating to the founding of modern probability theory. There were notions of probability in more ancient times, but most people tend to date modern probability theory to the Pascal-Fermat correspondence in the mid-1600s. And you can see this notion of probability in their correspondence. I like to ask myself, can I use probability in this way in different circumstances? Can I talk about the probability of whether a widget coming off the manufacturing assembly line is defective? Well, I need to be able to refer to a long-run, repeated set of observations that are the same thing repeated over and over, or that are essentially identical. So where is the long-run set of observations? It's the many products coming off the manufacturing line. Yeah, I feel good about talking about probability in this way, in this situation. Can I talk about probability when I'm talking about the life expectancy of university faculty? Like, what's the probability that a faculty member is going to live to be this age or that age? I initially included this as sort of a little joke to myself, but then I came to learn that people, at least at my institution and other institutions of higher ed, think very carefully about this. What is the life expectancy of their faculty? Can we talk probabilistically about this? What is the reference? What is the set of repeated observations, many repeated identical observations? Well, coin flips or manufacturing assembly lines may be one thing, but do we have really identical replications of the same thing? What is the reference to? Some similar university faculty in some way? That feels a little bit more wishy-washy to me. I don't feel as good about this application of probability in this way. What about this situation? The author of the disputed Federalist Papers. So the Federalist Papers were a series of papers, mostly written by James Madison or Alexander Hamilton around the time of the founding of the United States. There are a number of these essays, these papers, for which we know who wrote them. But there are, I think, about 12 papers for whom the authorship is disputed. They're not sure if it's Madison or Hamilton who was the author. Could we talk about the probability that James Madison was the author of these essays? What is the long-run repeated set of observations? These essays were written once. Right? What is the reference set of repeatable situations? I don't think there is one that allows us to use this interpretation of probability here. I don't think under this interpretation of probability, we can talk about the probability that Madison was the author of this essay or not. My guess is many of us were familiar with that notion of probability because that is what tends to show up in probability and statistics classes. there are other interpretations of probability. And I'm going to go over what is referred to as the subjective interpretation of probability, although I prefer the terms epistemic or degree of belief. Here's a quote from De Morgan, mid-1800s. By degree of probability, we really mean, or ought to mean, degree of belief. Probability then refers to and implies belief, more or less, and belief is but another name for imperfect knowledge, or it may be expresses the mind in a state of imperfect knowledge. In other words, we have different beliefs, and we want to quantify them. We have beliefs like, I think the coin is just as likely to land on heads as tails when I flip it. Or, I'm pretty sure that Martin Van Buren was the 8th president of the United States. Or, I am almost positive that James Madison was the person that wrote these essays of the Federalist Papers. Or, you know what, I'm not confident that it's going to rain here tomorrow. We are uncertain about things. Outcomes, results, or phenomenon vary or differ in unpredictable ways. Events may or may not occur. We assign a number called the probability to stand for our belief or our amount of uncertainty. So in this interpretation, probability is determined by the individual's belief. It is subjective or unique in the sense that it does depend on the investigator or other ancillary circumstances. It's not so much a property of the world as it's a property of an individual's state of knowledge, including their model of the situation. Different individuals in different contexts may have different beliefs, different background information, different amounts of uncertainty. The probability is just an expression of that uncertainty. So I live in Phoenix, Arizona. It's a desert. We have barely had any rain in 4 months. I would say the probability of that it will rain today is 0. Somebody else might say, well, the probability of rain in Phoenix is 0.1, like a 10% chance. Somebody else might say the probability of rain is 0.5, 50-50 chance. And still somebody else might say the probability of rain here is 1. It's certain to happen. We can't all be right. But these are all legitimate expressions of people's different beliefs. That is, these are meaningful statements. We see this interpretation of probability dating back to the modern founding of probability theory in the writings of Pascal, mid-1600s. This interpretation of probability has been around a long time. Can we apply it in different circumstances? Here, probability is an expression of our uncertainty or our beliefs about the situation. So it is applicable in events that are repeatable, as well as events that are not really repeatable. Can I talk about the probability of whether the widget coming off the manufacturing assembly line is defective? Yeah, I can. Can I talk about the probability of life expectancy for a university faculty? Yeah, I can. I have beliefs or uncertainty about that, and I can talk probabilistically about that. Can I talk probabilistically about the author of the Federalist Papers? Can I say, under this interpretation of probability, the probability that Madison was the author of these essays was 0.7? Is that a meaningful statement? Yes, it's an expression of my beliefs or my uncertainty. So what we're getting at here is, under this interpretation, probability is an expression of belief or an expression of our uncertainty. We can apply this in all sorts of situations. Things that have pretty reasonably well-defined, repeatable events for which there is a long-run stabilized relative frequency, as well as situations where that doesn't occur and we just have one-off or one-time events. What I would submit to you is that this is the way that we often use probability in everyday life. And here are some links to things like subjective probability from things like election forecasting or COVID forecasting or climate. Here, let me see if I can call this one up, get it going. Terrific. So this is from the World Meteorological Organization from spring 2022. I'll just read it here. Here, I can zoom. There is a 50-50 chance of the annual average global temperature temporarily reaching 1.5 degrees Celsius above the pre-industrial level for at least one of the next 5 years. I'm not going to get into the science of this. I actually am not qualified to evaluate the science of this. I want to talk about, does the sentence have meaning? There is a 50-50 chance of the temperature reaching something at least one in the next 5 years. As a subjective interpretation of probability, that is an expression of some set of beliefs. That is a totally legitimate expression. If I were to take the frequentist view, I would need to say, in order to make a statement like there's a 50-50 chance, I would need to refer to some long-run repeated set of identical conditions or events. This is the global climate we're talking about. We have not run the world, run history many, many times. It's happened once. There is no long-run repeatable set of events to refer to here. The context or the exact situation of the world right now has never been like this at any other time. We've not run this experiment over and over and over, per se. So I read a sentence like this and think, if I were adopting the frequentist lens on probability, I'd say, this is not a legitimate application of probability. You can't talk like this. But under the subjective view of probability, where probability is an expression of uncertainty or belief, this is a totally legitimate way to use probability. Why am I taking the time to go through this? A couple of reasons. One has to do with the kind of statistical inferences or inferential frame we make or adopt. So here's a little schematic where along the horizontal axis, we have our two perspectives on probability. The frequentist probability is defined in situations where there's a long run, repeatable set of events, the same thing over and over and over and over and over. The subjective or degree of belief view is probability is an expression of belief or uncertainty. Along the vertical axis is the kind of statistical inferential approaches that we could use. One is what you might think of as conventional or classical approaches, or frequentist sometimes, but I'm going to hold off on using that, or Bayesian. Conventional is the kind of stuff that you're used to seeing from most of your statistics training and experiences. And as we'll review in a little bit, frequentist views of probability go fairly hand in hand with conventional approaches to statistical inference. On the other hand, at least historically, the subjective view of probability has often been leveraged with or combined with Bayesian approaches to inference. Sometimes you will see people present things this way. Oh, as a Bayesian, I have to adopt the subjective view of probability. And what they are effectively saying is the Bayesian approach to inference is not compatible with the frequentist view of probability. You'll see this in writings where you say, in a Bayesian paradigm, probability reflects a degree of belief. Well, it can, certainly, that's this green check mark. But does it have to? I think the correct answer is no, it doesn't have to. A Bayesian approach to inference can be employed even when you as the analyst are using a frequentist view of probability. That is, there are people out there who say the meaning of probability is what is the long-run stabilizing relative frequency over many repeated events. That's the meaning of probability, and they still use Bayesian methods. It's more of a question mark about down here. Can you adopt the subjective view of probability and still use conventional or classical kinds of approaches to inference? And again, I think the answer there is yes, you can. I'm an example of this. I adopt the subjective view of probability. So over the next several sessions that we have together over the next few days, you will hear me talk about probability in this way as an expression of uncertainty, as an expression of belief. But I still do some conventional analyses that are not Bayesian, like I still do a t-test now and then, or I'll still do regular regression now and then. So I'm someone who adopts the subjective view of probability, but still uses non-Bayesian methods on occasion. So there are really 2 points that I want to leave you with about why I've taken a few minutes to emphasize this. One is, this is the language that I'm going to be using. When I talk about probability, I'm going to be referring to it as this reflects my beliefs about the situation. And we're going to see that. The other is because I don't want you to feel locked in. You will see in the literature people say, under Bayesian approaches, probability is interpreted as degree of belief. Well, that's often the case, but it need not be the case. There are plenty of scholars who say, I don't buy into that subjective degree of belief stuff, but I still use Bayesian methods.